As long as man existed, we have been fascinated with the workings of the human brain. And despite continued research, the brain's full potential and mysteries continue to captivate researchers. The Korea Brain Initiative is at the forefront of this research in Korea and a partner in a global project involving Korean, European, and Chinese scientists, which is providing a glimpse into the possibilities of a breakthrough future. Our globalist today, neuroscientist Dr. Bradley Baker, moved from the U.S. to Korea 13 years ago and is a member of the Korea Brain Initiative. He's here today to talk about his work in his newfound home and the fascinating world of the human brain. So, Dr. Baker, welcome to The Globalist.
Oh, thank you for having me. It's a real honor to be here.
Well, we're very happy that you made the time. I know you're the first neuroscientist we've ever had on our show, so it's a great honor. But tell us about your work, the Korea Brain Project. What is that?
Well, the brain is an extremely complicated thing, but on its primary source, it's just a basic electrical system. And so we study how the brain works at different levels, from the cellular level to the multicellular level, and understand how we respond to different environmental conditions, our behavior, and how we remember things and those sorts of things, which is so difficult to do that it requires a lot of people.
I know, but even that, that process, how, when something comes in, how we react, why we react in a certain way.
Well, let's look at it from a point of view like when you go to the doctor, right, and they hit your knee and it jerks out, right? Well, what actually is happening is you're just activating an electrical circuit that causes one muscle to contract, but at the same time, and this is extremely important, the other muscle has to relax. Because if they both contract, then it doesn't do anything. But to get movement, you have to have organized, coordinated muscle contraction, and that's your nervous system.
Okay.
So if you ever hit a light switch and nothing went on right, you just flick it sometimes. Well, now imagine you have millions and trillions of these light switches, and they're interconnected, and we try to figure out how they work together to mediate whatever response.
So the action itself may be a nervous system, but when you're talking about the control mechanism in the brain that tells all your nervous systems to do what it's supposed to do.
In a sense, but this one was just spinal cord, but there's a hierarchy of processes.
And at the top of the food chain is the brain.
Yes.
So when did the Korea Brain Project start, and how big is it?
The Brain Institute at KIST is 2011, I believe. So it's a relatively new, concerted effort to have Korea contribute to understanding how the brain works. Because without understanding how the brain works, then abnormalities may not actually be abnormalities, right? We need to know how something works in order to be able to compare it and make it better or treat it.
Within that project, what is your focus?
So neurons are like batteries. They have a plus and minus side, right? But it goes very fast. And so to study the brain normally, people use electrodes. But that means you have to be invasive, right? So you have to have a physical electrode wherever. What we want to do is convert it to light. Did you see Avatar, the movie Avatar?
Yes.
Yes. So when they made the connection in the original movie, right, they showed the brain and it lit up, different parts of the brain lit up. That's actually what we're trying to do. We take proteins from jellyfish that glow, so that when the brain works, the glow will change, and we can then see different regions of a brain or different regions of a cell responding to various stimuli.
So we're looking at what makes a light turn on.
Yes.
And what makes a light turn off.
Right, exactly. Yeah? And both are extremely important. People think that it's just activation, but actually inhibition is also incredibly important.
So, and why?
Well, for instance, when like when you reach for your glass of water, right? You reach for this, but you actually inhibit a lot of other motions. So there's a coordination of activation and inhibition. And when that balance is out of whack, then, like for instance, if it's too hard to activate, inhibition's too high, it's too hard to start and it's too hard to stop, and you get like these tremors, i.e. Parkinson's.
Yeah. So when you talk about your glass, for example, you know that your brain turns something on and off in a certain way so that your hand actually will go to the glass and pick it up.
That's right.
If it doesn't work, then you're not able to
right. Your control has varying degrees, right? So for instance, like if you step on your foot wrong for a long time and we call it fall asleep. I'm not sure.
Yeah.
So I mean, you can still walk, right? But the feeling back is altered, and so it's more difficult, right? So all of these processes come together, and somehow your brain deals with all of these different information. And when that information is altered, i.e. your foot's asleep, it becomes more difficult. Like I gave an example of too high of inhibition, but it also, the reverse can be true. The activation can be too easy. So you've heard of something like Tourette's?
Tourette's.
When they just spout.
You can't control what your movement is.
The inhibition is not high enough, and so you suddenly will. So it's the balance. It's not just activation or just inhibition. It's a balance between these two.
We were just talking a little while ago, and you said that when people find out you're a neuroscientist, there's one question that they ask you more than anything else, and I thought that was quite interesting. What was that question?
Oh, invariably, they'll ask me what's wrong with their brain.
What's wrong with my brain?
Right, because you're with yourself 24/7, right? You know all the smart things you do, but you also know all the dumb things you do, and you're like, why did I do that?
Yeah. So it's what's wrong with me?
There's nothing wrong with you. Everybody experiences these things, and just the variability from day to day of how the brain conceives these inputs, right? And we're very flexible. For instance, you walk into a room and there's a fan going, right? You hear it, but after a few minutes, it goes away.
Okay.
Why, right? You go swimming, you jump into the water, it's cold, right? But after a few minutes, it's no longer cold. And so the brain is constantly monitoring for novelty, right? And this is why you tend to forget, or one of the reasons you tend to forget.
Let's take it in terms of if I asked you what's wrong with me or what's wrong with my brain, it would be like some days on this show, I come in and, I'm not prepared, but sometimes it clicks. I can ask the wonderful questions and the rapport is great. Sometimes I prepare well, but it's like pulling teeth and I can't focus.
Right.
What's wrong with me and how do I fix it?
There's nothing wrong. That's just called being human. That's how the brain works, right? It's processing so many different things, and for whatever reason, there might be something that's distracting you, or there might be you didn't sleep well last night. All these things could be variables that we all experience, right?
But knowing this will help me become better?
Maybe not.
No, but maybe not. I don't know what we're doing here.
I haven't gotten better at remembering things.
Because you're a neuroscientist, can you
I'm terrible.
Remember things better than anybody else?
No, but what I can do is I can relate better. It's like, this is just neuroscience.
So you're just sort of making the
I make a better
term.
excuse. Yeah, that's what I do.
Oh, okay. That's a good function. Yeah. What has been the most phenomenal breakthrough recently in this study of the brain?
So I'll give an example that many people are cognizant of right now. I would say artificial intelligence, right? So you would be surprised that coding is a result of neuroscience, but actually the artificial intelligence got its name because they used neurons as a model of its computing power to develop these logarithms or algorithms to do these sorts of analyses, right?
So they're using the computer that matches what a brain does.
It's modeled. I mean, it's not my
What a brain
expertise.
does,
Yeah.
So that was possible because you were able to figure out as much as you...
Well, as you understand how neurons start to compute information, and it enables novel ways to develop technologies to process information.
So by understanding these kind of things, for example, AI is going, people talking about AI will change our life. But what are other ways in which the study of the brain will change our future?
You see, like Alzheimer's steal people's memories, and when you talk to an Alzheimer's patient, my grandmother had Alzheimer's, and suddenly she was back on her farm from long ago, right? So it didn't steal her memory, but it kind of altered her perception of, was this a memory or was it real, right? And so what I would hope is that we start to have a better understanding of how we perceive consciousness now versus memories in the past that will give rise to different sorts of treatments, and maybe not just drug treatments, but behavioral treatments to compensate different brain diseases.
So to combat Alzheimer, not just through medicine,
absolutely.
but through action.
Yeah, absolutely.
Through brain exercises.
And it could also be diet, right? Recently, like the gut biome, it matters what's in your gut as how your brain behaves, which is remarkable to me. So all of these connections, right? But then that would offer even another sort of treatment.
Because we're at that stage, is it also one of the reasons that I was reading in Nature magazine that international collaboration between these mega projects are more important than ever before?
Right, and of course collaborations are extremely important, and international collaborations especially, but since I've been a scientist in Korea now for 13 years, one thing that I've come to appreciate is the cultural differences. And science is basically science, right? But there are different approaches from different countries, and merging those can create a much better approach to address a problem than if only the United States did it, or if only Europe did it, or only Asia did it. Having these diverse approaches, at least for me, has made my science much better. Yeah.
Now that you've been here in Korea for 13 years, what is the uniquely Korean approach?
There's more of a group effort in Korea. And it's top down, and this is sometimes good and sometimes not as good as the others. But my Korean pronunciation is still very terrible. Woori, the one. One. I mean, there is a feeling of one that we try to incorporate, but sometimes you don't fit so well. So there's some positives and negatives about this approach. But in general, it's been great for me because, again, we make tools to help so we can be Woori a little bit easier than other potential scientists.
I hear there are non-Koreans working in Korean labs a lot, but there are not many that continue to work for 13 years.
Right.
What brought you to Korea, and why did you stay so long?
When I interviewed, I was really only interested in discovering the interview process. And a colleague George Augustine, had a new center at KIST, and he was recruiting foreign scientists. So he's like, come see. And I'm like, okay. I didn't take it that seriously, to be honest. But I came, and I was like, there's no way I'm taking this job. It's halfway around the world and all that. But I got to Korea, and I saw where I would have my own lab, right? And then really, what I think the real strength of Korea is its energy. The energy of the people, and it's impressive how well the energy is managed here and how it's focused towards certain problems. Now, that doesn't mean that it always solves the problem, But that was one of the big, I do remember, I'll always remember that, being struck by the energy of this place.
How did you notice it? Did people move faster? Or?
Well, I mean, of course, but I mean, to me, Korea is still a young country, right? It has an ancient culture, strong heritage, but it's, 1953, 54, so it's only less than, yeah. So when I look at the United States, which I love my country, but to me it's like late middle age and getting kind of grumpy, and Korea is still trying to like prove itself on the world stage and aggressively going after problems and recruiting and education. It's all these things really contributed to me coming to Korea. Yeah.
And because Korea kept you here for 13 years, it meant that there were more, I guess, successes than disappointments?
Oh, so if you look at my publication history, Korea has been great for me. It sounds bragging, but I'm really surprised at how well we've done, the advances we've made. We have seen some things that I never even imagined. Right? So we were talking about, we study neurons, we study cells, but inside neurons are proteins, and we are starting to see how proteins work and move. That wasn't really the intention of our, but we started to see it, and we're trying to manipulate it to make better tools. So I've just been really happy with the progress that we've made. Yeah.
I also hear, the Korean scholars always talk about the fact that you name your achievements give them Korean names.
Yeah.
Is that usual or?
No. So when you make a probe, right, part of the thing is you want the scientific community to use it. So one thing, you have to come up with a name that's memorable, right?
Okay.
So Korean words in the scientific community are new, right? So if I name a probe 2X47, right, people are going to forget that.
Yeah.
But if I name a probe Pado or Nabi, there's a better chance of them remembering those names. So that was one thing. The second thing was
Pado meaning
wave,
Pado meaning wave, and Nabi meaning butterfly,
yeah.
which are actually wonderful names,
right.
but
And
not usually put on a scientific.
Right, well, so these are proteins, and actually the behavior of one protein looks like a wave, so we call it Pado.
Okay.
The other protein has two fluorescent proteins on its ends, so it's kind of like a butterfly. So we do try, so we have Ilmol, sunset. Yes, so because it's red and it gets dimmer. We have Sonagi, because it's very fast and it goes down it's a very fast down. So I always kid, my goal is to make the world speak Korean, right?
Yeah.
So but the real reason was, it was just when we started out, I wasn't sure how successful we would be, right? And I was just very grateful that we had a chance to do this research. And so just to say thank you to the Korean government for allowing us to do this research, we would give our probes Korean names. And I have some Korean names I can't pronounce. So when I give a talk, if I'm in the US, it's okay because they don't know.
Yeah, they don't.
But in Korea, I can see a little bit of cringe.
Yeah, people. I mean, but now you are a Korean scientist, even though your nationality here, but you're part of the Korea team, really, Team Korea. What are the strengths? I mean, you talked about the group, but are there other things that position Korea in a unique way versus teams of other countries?
First thing I would say are the students. Now, we have international students, also great, but the Korean students, very good. I was just in the States for a meeting, and everyone's asking me to send them their Korean students because they really perform very well. So education-wise, very strong. The other thing that Korea does is group approach. For some places, I think the universities have more of an individual, but for the Institute, there's more of a group approach, and that forces you to think about things in a different way. Now, for me, that's been good, but for some scientists, it could be a negative. Right? So it's hard to say this is a total positive or total negative. Yeah.
What does that mean? Thinking about it in a group versus not.
As a scientist, right, you start to think about, okay, I know how my proteins behave in this, but they're looking at behavior. They're looking at disease. How does these two things merge, and how can we create a research approach that would incorporate both of these things. And would that be better than just doing this and just doing that? Sometimes just doing this and doing that might be better, but you can also see how combining these two things would give a unique approach that could lead to different sorts of solutions that wouldn't happen.
So is it more like an outcome-based kind of?
I know, so I would strongly discourage outcome-based, although the world really, the scientist in me, I think it's an approach-based, right? And because if you have a strong approach, there will be a positive outcome. Might not be the outcome you want, but there will be an outcome that will lead to a better understanding. Yeah.
You talked about, other institutions wanting more Korean students and talking, but we've been talking to a few people saying that Korean students are top of the line in many areas, but there's a lack of women in your field. Do you notice that as well?
So no, but of course I do, especially in the States. But I haven't been to many universities in Korea, but at KIST, I must say I've been very impressed. I don't know what the actual numbers are, but there are a significant number of female scientists at KIST. So I think Korea is doing a fair job. I'm certain it could do better, right? But I think Korea is above the curve than other countries
really?
I mean, just from my experience at KIST.
Yeah.
Right.
So at least it's a common issue, not just in Korea, but in other countries.
Yes, absolutely. I mean, in previous years, I don't think the encouragement was there to do this. But now, at this day and age, I mean, my daughter's now, 26.
Wow.
She, to watch her explore, right? And that's really what science is.
Yeah.
She's a political science person, but to watch
Exploring
her explore
a different area.
Yeah, exactly. Watch that exploration happen, right? Is really rather fun, I would say. Yeah.
Now, on your research now, what is next? What is the next name that you're thinking of?
Anpak.
Anpak.
Anpak, in and out.
In and out?
Yes, because our lipid, in some parts of the cell, the lipid environment is different, and our protein works in this lipid environment and not that lipid environment. So it's in and out of the voltage field, and this is why it works. So that I'm very happy with that name, actually. It's
really?
actually
Okay.
applicable. And then we have to understand what that means, because this organizes the cell in a way that we had not been familiar with before, because we couldn't see it. But now with our fluorescent probes, we can see it. And so we'll have to see what that holds in store.
All right. So ultimately, I mean, is there like an impact you'd like to make on the world type of thing?
Oh, of course. I mean, I just recently discovered this. As one of my students, sort of an honorary student that was in my lab for a smart period of time, just opened up his own lab at Yale University, right? At Yale Neuroscience Department. And I cannot tell you how meaningful that is to me, to watch your students become better than you at science and see them continue on in their own efforts. And then, so I think ultimately, of course, I would like to have some scientific breakthroughs, but ultimately I would like for my career to be known that I was a decent mentor and had an influence on many different scientists. Yeah.
And the whole generations of you made the world a better place.
Hopefully.
Made us better people, human beings.
Hopefully, yes.
Right. Well, thank you very much for taking the time and tell us that. I hope you reach that goal.
Oh, thank you. It's been a great pleasure. Thank you for having me.
Thank you. And that's it for me. I will be back next week with another globalist who's putting Korea on the map. Sonji, out.